Myself Dr. S. Radhika, Associate Professor, Department of EEE, Satyabama Institute of Science and Technology, deemed to be University, Chennai. In this video lecture, we are going to derive the equation of transmission line from the sending end. First, let me tell you what a transmission line is. Transmission line is a means for transfer of electrical energy or power from one place to another. It can be used for transfer of communication signals from a transmitter to a receiver, or between an antenna and a receiver, or a transmitter and a receiver, and vice versa. So, before going into the derivation part, let me first take up the equivalent circuit of a transmission line. So, for this we are going to take the simplest form of transmission line, which is a two-wire line. So, this two-wire line is made of two conductors separated by a dielectric medium, usually air medium. So, we have two conductors, conductor 1 and we have the second conductor, conductor 2. So, this setup you call it as a parallel wire line or a two-wire line or an open wire line. So, if I pass a current, if a current of I is made to pass through this conductor, we find that there is a magnetic field around this current carrying wire. So, this magnetic field can be illustrated by means of our series inductor. So, due to this current flow, there is going to be some voltage drop across this conductor, which can be illustrated by a series resistance. And this setup, that is two conductors separated by a dielectric medium, can be made to a capacitor, which I have drawn it here. And always this capacitor will be lossy. To illustrate that, we have added conductor G. So, this setup, this entire setup, which is made of a series inductor, a series resistor and a parallel capacitor and a conductor, make up the equivalent circuit of a transmission line. And this inductor and resistance put together can be called as series impedance Z, which I can write it as R plus j omega L. This parallel combination of capacitor and conductance can be called as admittance Y, which can be written as G plus j omega C. Thus, the equivalent circuit is made of a series impedance term made by resistor and an inductor, and a shunt admittance term made by conductance and capacitance term. Let us start with the derivation of transmission line equation. So, for this, let me take a transmission line of length L. So, this instead of taking the entire length L, I am going to take an elemental length dx, which I call it as PQ. So, this elemental length dx is going to be at a distance of x from the sending end. Let me take the sending end parameters, that is Vs as the sending end voltage and Is as the sending end current. So, these two parameters are now going to be used, and I am going to derive the voltage and current at any point on this transmission line using this sending end parameters. So, now this elemental length ds, I have replaced, that is this PQ, by the equivalent circuit which we have derived earlier. From this equivalent circuit, we have the series impedance term and the shunt admittance term, which I have drawn it here. So, now using these parameters, now I am going to start with the derivation of transmission line equation. At the point P, let us take the current and the voltage be I and V. At the point Q, let it be I plus di and V plus dV. The change in voltage for the length PQ is the difference in voltage at point P, which is V, and the voltage at point Q, which is V plus dV. So, V minus V plus dV is equal to the impedance term, which is R plus j omega L. For the elemental length dx we are taking, so it is dx into I. Similar way, if I say for the change in current for the elemental length dx is going to be I minus I plus di, which is equal to G plus j omega C, which is the admittance term, which is multiplied by voltage into dx. So, from this two equations, I can able to get the differential voltage term, which is dV by dx. That is, if I bring this dx to the denominator, I get minus dV by dx, which is equal to R plus j omega L into I. Similar way I can able to get minus di by dx is equal to g plus j omega c into v. So, what I am doing here is after this I am differentiating the equation number 1 and 1 by with respect to x. So, that I get two more equations, that is d squared v by dx squared is equal to r plus j omega l into di by dx and minus d squared I by dx squared is equal to g plus j omega c into dv by dx. Let me call this equation as equation number 2. So, after this I am going to substitute equation number 1 in equation number 2. So, when I substitute, that is the left hand side of equation number 2 becomes g plus j omega c into v. So, on substituting I am going to get equation number 3. If I replace, that is if I substitute a propagation constant as r plus j omega l into g plus j omega c, I get an equation. So, this equation, that is d squared y by dx squared is equal to p squared v and d squared I by dx squared is equal to p squared I is called as the differential form of transmission line equation. So, this differential form of equation is one form of equation of a transmission line which we will be using it for obtaining the general solution. So, the differential equation is a second order differential equation with constant coefficients. So, the general solution is v equal to a into e power px plus b into e power minus px, and for the current it is going to be I is equal to c into e power px plus d into e power minus px, where we have 4 unknowns or the 4 constants called as a, b, c and d. So, what I am going to do after this is I am going to differentiate this equation 5 with respect to x again. So, that I will be getting equation 6. Equation 6 is dv by dx is equal to, when I differentiate e power term with respect to x, it becomes p into a e power px and this minus comes here which is b into e power minus px. Similar way I get one more equation for the differential current element, and I am going to substitute equation number 1 into this equation 6. So, that I get equation number 7. So, from this equation number 7 I have the propagation constant available, which I am going to replace it by the propagation constant. On substituting the propagation constant into this equation number 7, we have got equation number 8, where we have replaced the propagation constant by the series impedance and the shunt admittance term. So, if I am going to introduce one more constant called as z naught, which is equal to square root of r plus j omega l divided by g plus j omega c, which I call it as the characteristic impedance. If that is substituted in place of this equation number 8, we are going to get equation number 10. That is we are going to have it as, that is this term is going to be replaced by z naught. So, still equation number 8 and equation number 5 are going to be as function of the unknown constants a, b and c, a, b, c and d. So, in order to eliminate the unknowns, I am going to substitute the boundary condition, that is at x equal to 0, the voltage at the sending end becomes Vs and the current becomes Is. If this is substituted, I am going to get equation 9 and 10. So, this equation number 9, where I have replaced my voltage V as Vs and the exponential term becomes equal to 1 because e power 0 is 1. And similar way, I have replaced this r plus j omega l, g plus j omega c under the square root by the propagation constant term, which on substitution gives the equation number 10. So, I am going to now use this equation number 9 and 10 to solve and get the equation, that is an equation which correlates A, B, C, D in terms of the sending end parameters, that is the sending end voltage and the sending end current. So, these two equations I have written it again, that is equation number 9 and equation number 10, I have written it here. So, if I take the first equation from equation number 9 and the first equation from equation number 10, and if I solve for, that is if I add these two equations, I am going to get equation number that is the constant value of constant B. If I subtract, I am going to get the value of constant A. Similar procedure if I adopt, I am going to get constants C and D. Substituting these constants in equation number 5, I am going to get this equation. So, from this equation I am going to eliminate, that is this Vs is taken as common term which is available here, and this e power exponential term is brought inside the bracket. So, similar way I have done it for Is z naught, which I have taken Is z naught outside and is left with the exponential term inside the bracket. So, actually what is this e power px plus e power minus px by 2 is nothing but cos that is hyperbolic cos function. So, I have written it as cos h px. Similar way e power px minus e power minus px by 2 is nothing but sin h px. So, the final equation now we have got, that is V is equal to Vs cos h px minus Is z naught sin h px, which is nothing but the equation of a transmission line, that is the voltage at any point on a transmission line is now written in terms of the sending end parameters, that is sending end voltage, sending end current, and the two constants z naught and p, and this x is nothing but the distance of our elemental length from the sending end. Now, we are going to use the same procedure to get the equation for the current. Similarly, if I substitute the unknowns, that is constants C and D into the equation number 5 for current, we get this equation where I have replaced constant C by Is minus Vs by Z naught by 2 and constant D by Vs by Z naught plus Is by 2, and of course, I have multiplied these two terms with the exponential term that is available. Similar to what I have done for the voltage, I have done for the current here. I have taken Is outside. So, you are left with e power px and e power minus px. I have brought this 2 inside the bracket. Similar way, I have taken minus Vs by 2 z naught outside the bracket. I am left with e power px minus e power minus px by 2, and this exponential term is nothing but the hyperbolic trigonometric function, that is I is equal to Is cos h px and minus Vs by z naught is written, and this e power px minus e power minus px by 2 is nothing but the sin h px term. Thus, V equal to Vs cos h px minus Is z naught sin h px and I equal to Is cos h px minus Vs by z naught sin h px are the equations of the transmission line in terms of sending end parameters. So, now we have voltage, we have current, which are nothing but the voltage and current at any point on the transmission line, and we have, and this voltage or the current is written in terms of Vs. Vs is the sending end voltage and we have Is. Is is the sending end current, and this hyperbolic term involves P, which is the propagation constant, and it also involves Z naught, which is the characteristic impedance, and x is nothing but the distance of our elemental length from the sending end. Similar way, we have written for current, where current at any point on the transmission line is function of the sending end current, sending end voltage, characteristic impedance, as well as the propagation constant and function of x, which is the distance from the sending end. So, now having derived the voltage and current at any point on a transmission line in terms of sending end parameters, the next lecture we will discuss how to derive the voltage and current at any point on a transmission line in terms of the receiving end parameters. Thank you.